Hi, this is the 6th week of our chemistry course, and today we're going to go ahead and finish unit number 1, which is the Big Bang. And today's topic is going to be the history of planet Earth, as well as calculations for half-lives. So we're going to work on those today. Our objective for our lesson, students will learn how to figure out the age of our planet. Also, students will learn how to do calculations for half-lives. So let's start with the history of our planet. Continental rocks, so some of the rocks found on top of the continent, not at the bottom of the ocean. So continental rocks are as much as 4 billion years old. And they're much older than the rocks that are found at the bottom of the ocean. They're around 200 million years old. Why are those rocks at the bottom of the ocean younger? The reason is because they've been recently made in between the plates at the bottom of the ocean, where the plates are where they meet. New rocks are generated. Now, the oldest rocks found on Earth are in Australia, though Canada has recently claimed that they have older rocks. Though Australia has rocks that are about 4.4 billion years old. The Earth itself is believed to be somewhere around 4.5 billion years old, give or take 50 million years. How is that determined, though? Alright, and the answer is half-lives. That's how the age of our planet was determined. So what is a half-life? The spontaneous radioactive decay followed a characteristic exponential decay law. What that means is that it is very predictable the way that a radioactive substance will decay, will break down. So some of these rocks that they're measuring in Australia and Canada, what they will measure is the element for uranium. And uranium will have a half-life of 4 billion years. What that means is it will take 4 billion years for half of that element to decay. So when they get these rocks and they see that roughly about a little bit more than half of that element has decayed, then they can make the calculations for how old that rock is. And that's what leads us next into a half-life. How is that calculated? So that's our next topic. Alright, nuclear half-lives are solved using these equations right here. So half-lives allow radiometric dating, so to figure out how old something is based on how much radiation they have. And that is used for the rocks that we've been talking about, and these are our two equations. Now let's get into them a little bit more. Nt equals No, 1/2 to the power of n, where n equals t over t 1/2. What are all of those? Well, let's start with Nt. Nt is the mass after some time has gone by. And O, that's the mass at time 0. That's what the O is. N is the number of half-lives. T is the amount of time that's gone by. And T and a half, that is the length of a half-life. Alright, so this graph should give you an idea of exactly how does a half-life work. So let's say we have 100% of an object that is radioactive. How long would it take for half of that object to go away? So you notice from here to there, half of them are gone. Well, that amount of time, that is referred to as a half-life. So that'll be 1 half-life. Now, 50% of it goes away in 1 half-life. Now, what about after 2 half-lives? Will 100% go away? No, only half of the half will go away. So now you're down to 1/4. So the original was 100, now you're down to 50, now you're down to 25, maybe 12 or 13, and so on will continue. Maybe 7 will be the next one after. So it'll be half, and then you cut it in half and half. So those are half-lives. Depending on the element, some elements have a half-life as short as a few seconds. Other elements, like I mentioned, uranium, has a half-life of 4 billion years. Alright, so now let's get to our first example right here. Let's talk a little bit about carbon dating. Carbon dating is something that is used to figure out the age of something that was alive, something that is organic. For example, an animal, like here they have a dinosaur, or a tree or grass. Carbon dating is used to find their age. How does it work? In it, you have the sun, it emits cosmic rays, it reacts with nitrogen in the air, and that will eventually create carbon-14. The normal carbon that we're exposed to is carbon-12, but there are some trace amounts of carbon-14 in every organism. That carbon-14 goes into the plants, they go to the soil, the plants absorb it from the soil, the animals either eat the plant and another animal eats the animal that ate the plant, and eventually it ends up inside of an organism. Now, let's say that the organism dies. It's no longer taking in carbon-14 because it's not eating anymore. It has died. So at that point, the carbon-14 is going to begin to drop inside that organism. So what a scientist will do is figure out, well, how much carbon-14 is left. If there's a lot left, then that means that animal has recently died. If there's very little left, then that means that animal has died a long time ago. The half-life of carbon-14 is roughly 6,000 years. So in this problem, they ask you as the following. An 800-gram sample of carbon-14 has a half-life of 6,000 years. How many grams of the element will remain after 30,000 years have gone by? Alright, now there's two ways to solve for this. One is a little bit more work but easier math. The other one is more math, which is slightly more difficult, but it takes less time. Alright, so I'm going to solve it both ways, so you can use whichever one works best for you. Alright, so we're going to begin with writing down everything that we have. At time 0, the mass was 800 grams. After some time has gone by, the mass is going to be, well, we don't know that. Now, the half-life is given right here. The half-life is 6,000 years. So I'm going to put T with a small 1/2 right here, 6,000 years. So that's how long it takes for half of the carbon to go away, 6,000 years. So the amount of time that went by is 30,000 years. So I want to know if that 800, how much is left over after 30,000 years. Alright, so that's our given. We're going to go ahead and figure out what is our number of half-lives. How many half-lives went by? And to do that is just divide time over the half-life. Time was 30,000. The half-life is 6,000. So the answer is 5. 5 half-lives have gone by. Next, we're going to go ahead and plug it into our formula. So for this one, that's what we're looking for. How much time has gone by? Oh, I'm sorry, how much is left over of the sample? The original sample had a mass of 800 grams. And the N is the number of half-lives that's gone by. We've had 5 half-lives that's gone by. So in your calculator, you would put 800 multiplied times 0.5 raised to the 5th. And that will give you your answer. Another way of looking at it, you might say, well, it's 800 times a half, times a half, times a half, times a half, times a half. Notice I put it 5 times because it is to the 5th power. Alright, so let me put it into a calculator. The answer is 25 grams. That's how much remains after 30,000 years. Initially we had 800 grams. After 30,000 years we only have 25 grams. So if a sample only has a small portion of it, now you can figure out, well, how long was it there? This problem could be solved backwards to figure out the time, and we will have some like that. Alright, so that is carbon dating. Alright, now, I mentioned I was going to solve it 2 different ways. This is a little bit more mathematical. Another way you could do it is more of a table. In the table, I like to put the mass, and the time. So, what was the initial mass? 800. That was at time 0. 0 years have gone by. Now we're going to do every half-life. We cut this number in half. Alright, so let's say 1 half-life has gone by. So, let's move it down. That's 400. From 800 to 400. How long did that take? Well, the half-life takes 6,000 years. So, if 1 half-life went by, that means 6,000 years have gone by. And then you keep on going. Half of 400. 200. Oh, that's another half-life. So that means I need to add another 6,000 to this. Alright, so that's the next one. Keep going. Alright, half of 200. 100. So I add another 6,000. All right, and you keep on going. How long do I keep going, by the way? Until I reach this time. 30,000 is what we wanted, right? How much is left over after 30,000? So let's keep going. Add another 6,000. We got 24,000. So half is left. That's 50. And last one, another half-life. Half of 50 is 25. And add another 6,000. So that'll give me 30,000. So there you go. After 30,000 years, we have a half-life of 25 grams. Alright, that's our mass. So it's the same answer, just completely different method. Which one's better? Well, whichever one works for you is better. Though this one does have its limitations. What if I ask you, how much of the mass is left over after 200 half-lives? Would you really want to go 200 lines down? No. At that point, the formula would definitely work better for you. Let's move on to the next example. In example 2, we start with a cartoon. We have a carbon atom and another carbon atom, and they're sitting there, they're watching TV. What do you call this? That's called carbon dating. Alright. Now, let's move along to the example. A 96 gram sample has a half-life of 6 months. How many grams of the sample remain after 4 half-lives have elapsed? Alright, so let's go ahead and write down all the information that's given to us. Alright, the original mass at time 0, it is 96 grams. Alright, they want to know how many grams are left over again, so question mark on NT, the amount. Alright, the half-lives, how many half-lives have gone by? 4 half-lives have gone by, and each half-life is 6 months. Alright, so how much time has gone by? You don't need that number to solve for this problem. And but if you really wanted to, you would just multiply the number of half-lives times how long each one takes. So 4 times 6, so it'll be 24 months, about 2 years. Alright, but they didn't ask us how long this problem would take, so we don't really need this number. We have the n. Alright, so let's go ahead and solve for it mathematically. For this one, it'll be nt equals no, 1/2 to the power of n. Nt is what we're solving for. No was given to us 96 grams. How many half-lives went by? There are 4 half-lives that have gone by. Alright, so you multiply 0.5 to the power of 4 times 96. The answer for that one is just 6 grams. Alright, so we got our answer. Alright, next, how would you solve that as a table? Well, much the same way. Let's see, I would start with 96. This is our mass. And the time, you always start the time with 0. And let's see, half-life to 6 months. We don't even need that. We all just need to go 4 half-lives. So that'll be our first one. Half of 96 will give you 48. That's 1 half-life. Our second half-life, half of that is 24. Our third half-life is half of 24 is 12. And our fourth half-life, see they told us 4 half-lives went by, that'll be half of 12 will be 6. So 6 grams. So there's your 2 separate methods you can do it. They didn't ask how long this would take. That could be a test question, so let's go through it. Well, there's 4 half-lives and each one takes 6 months. Well, then that'll be 6 months. Then add 6 more, that'll be 12 months. And that'll be 18 months. Oops, I'm sorry, you got 1, 2, 3, and 1 more because it said 4 half-lives. So 24 months. They didn't ask for that, but there you have it. This whole reaction will take 24 months. Alright, let's go ahead and move along to our third example. On this example, they ask you guys, a 320 gram sample has a half-life of 11 minutes. How much time needs to elapse before the sample degrades to 40 grams? Alright, so now you're looking for time in this one in particular. Alright, I wanted to go ahead and mention the picture right here. In the picture right here, you see a scan of someone's brain. And what doctors will do sometimes is they'll give the patient a drink, and that drink will have a radioactive element to it. So they'll drink it, and yeah, it's radioactive, but it degrades very quickly in minutes. It starts breaking down. What that will do is it'll create a glow that the machines can pick up all over the person, and the radioactive material is in the person's blood, and it goes around, well, wherever blood goes, which is pretty much anywhere, except though if you had a stroke. A stroke is when a blood vessel into the brain gets blocked, and when it gets blocked, blood cannot access that area of the brain, and without blood to that area of the brain, that piece of the brain could die. So in here you see the diagram, there it is, that spot right there, it's not getting any blood. So now the doctor knows, I know exactly which part of the brain is not getting any blood, so now I can get in there and hopefully unplug it. It is clogged up, and the blood will reach the rest of the brain, and the brain will be healthy. If they do it quickly enough, they could save that piece of the brain. If that piece of the brain dies, the person might lose function over some parts of their body. May they not be able to move the left side of their body. They might not be able to use maybe certain pieces like half of their mouth. And so if they get to a person quick enough, they could hopefully save them. Now, why do they want to isolate exactly where it is? The doctor doesn't really want to go poking around the brain just guessing where the issue is, because they might cause more damage than the actual stroke. So that's why I want to pinpoint exactly where is the problem. Alright, so now let's get to this example. A 320 gram sample has a half-life of 11 minutes. So there's our half-life, 11 minutes. How much time needs to elapse before the sample degrades to 40 grams? So times 0 is 320 grams. And the next one is 40 grams. Alright, so how much time needs to elapse? Now, let's talk a little bit of math. I'm going to go ahead and solve it. So here's our formula again. And what I need to get is that n right there. And once I have the n, I can multiply it times the half-life to get the time. Alright, so you start working on it. The 40 goes here. 320 goes there. And now all you got to do is isolate the n. Now isolating the n, you move the 320 over here first. And then isolating the n is going to require logarithms. Now in logarithms, this chemistry is a 10th grade class yet. I'm not 100% sure that your math teacher has gotten to logarithms yet. So I'm going to stop right here and say this is not the best way to solve it. I'd rather use a table method to solve for how much has gone by. Alright, so I'm going to start with 320. Alright, so that is our mass. Alright, so after one half-life, how much do we have? Half. So that's 160. After two half-lives, how much do we have? Half of 160. 80. After three half-lives, half of 80 is a 40. And notice, there you go, I have my 40. Alright, and so it took three half-lives. Now that I know what that is, to get time, remember the formula was n equals t over 1.5. So if I move the 1.5 here to get the time, I just need to multiply the half-life times the number of half-lives, which was 1, 2, 3. 3 was the number of half-lives. So in this case it would be 11 minutes times 3 half-lives. This whole process will take 33 minutes to get it down from 320 to 40. So that will be our answer. 33 minutes. Solving for that 33 minutes here, again you need logarithms, and that is just outside of the scope of our chemistry class. Alright, example 4. They ask you guys with just a graph, find the half-life of this. Alright, our initial quantity is 7. So how long is the half-life? Well, half-life is the amount it would take to get to half of the original amount. The original amount is 70,000, right? So what's half of 70,000? 35,000. So I'll find that right here in the middle. go across. You see where it hits the line, goes down, and that is 6 hours. So that's how you would get half-life from a graph. It is your starting amount, whatever half of it, wherever that is, go across, down, get the time. The time's at the bottom. The half-life of this sample is 6 hours. Alright, we're going to go ahead and move on to our last example. This is example 5. In this one they ask you, as a substance has a half-life of 21 days, how many days would elapse before the substance decreases to 1/16 of the original quantity? 1/16 of the original quantity. Alright, so this problem, we're going to go about a completely different way of solving it. I'm going to ask you, alright, one half-life is the amount for half to go away. So how many half-life would you need to get 1/16? So let's see. That would be one half-life, right? And if we add a second half-life, what's that? 1/4. What if we add 3 half-lives? What was 2 times 2 times 2? That's an 1/8. What if we had 4 half-lives? Two times 2 times 2 times 2, that would be a 16th. So that's 1/16. So how many half-lives would you need to be 1/16? You need 4 half-lives. So pretty simple way of going about solving this problem. You need 4 half-lives so it can be 1/16 of the original amount. And each half-life is 21 days. So how much time would that take? It would be the half-lives multiplied times the number of half-lives, and that'll give you the time. Alright, so time equals n. N is 1, 2, 3, 4. 4 half-lives multiplied times how long each one takes, the half-life of each, which is 21 days. So that gives you 84 days. That's how long it would take to go down to 1/16 of the original amount. Alright folks, so that takes care of our lesson. We've gone over the age of the Earth, about 4.5 billion years old, how it's calculated using radiometric dating. And we also talked about all the calculations that were used for half-lives. Alright, that brings us to the end of this section. Thank you so much for watching.